This lecture is from zero order reaction. Zero order reaction. You know that order of reaction is the power of the concentration terms appearing in the rate law, appearing in the rate expression. So, zero order reaction means a reaction whose rate varies at zeroth power of the concentration of the reactant. Like this, a zero order reaction. Suppose minus dc by dc, this is the rate of reaction. So this is proportional to concentration of reactant, power zero, or this is equal to minus dc by dt. This is equal to constant k naught. K naught is the rate constant of zero order reaction into C naught. And C naught anything power zero means one. So this is minus dc by dt. This is equal to k naught. This is a constant. Thus, the zero order reaction is one whose rate remains throughout constant, whose rate remains throughout constant. From beginning to end, the rate remains constant. Thus, a zero order reaction, a zero order reaction is one whose rate remains remains throughout constant, throughout or constant. Actually, rate remains constant. Why rate remains constant? The rate remains constant because the reactant concentration remains constant. The constancy of rate, the constancy of rate is due to constancy of concentration, concentration of reactant. During zero order reaction, during zero order reaction, the amount of reactant decreases with time, with time, but the concentration remains the same. Remains the same. There is no increase. There is no increase in the concentration. There is no increase in the concentration of there is no increase in the concentration of reactant, concentration of reactant upon addition of upon reactant into into the reaction into the reaction mixture. Reaction mixture. That is, the rate is that is the rate is independent of the concentration of the reactant. But to be more correct, but to be more correct, more correct, it is not possible, it is not possible to increase the concentration of reactant, the concentration of reactant upon addition of reactant, reactant. The concentration always remains maximum, always remains at maximum. Always remains at maximum. An example, if you plot rate of reaction versus this is rate versus time, then the rate will be this time, rate will remain throughout constant, like this, throughout constant. And this throughout constant, and this rate is what? This is equal to K naught. K naught is the rate constant of for a reaction, zero order reaction, rate constant of zero order reaction. Okay. Now we have to see that why concentration always remains at maximum. As concentration does not increase upon addition of the reactant in the reaction mixture. This can be explained by taking an example. Example of zero order reactions are examples. The decomposition of HI, ammonia gas upon gold surface, on gold surface, and NH3 gas, gold, you get N2 half plus 3Y 2S2 gas. This is gas. Another example is the decomposition of HI gas upon gold surface. Decomposition HI gas upon gold surface. 2HI gas, gold, H2 gas plus I2 gas. Similarly, another example is decomposition of nitrous oxide gas N2O upon gas N2O gas upon platinum surface from platinum surface. Gas is decomposing into N2 is twice N2 plus O2 plus O2. N2 is gas, O2 is also gas. Now it should be remembered that it should be noted that the decomposition of HI upon gold and decomposition of N2O upon platinum both are zero ordered in presence of gold, in presence of platinum, that is in presence of metal surface. But in absence of metal, when no catalyst is used, metallic catalyst is used, then they behave as second order reaction. In absence of metallic catalyst, the decomposition of HI gas and N2O gas are both second order reactions. Now we have to explain. Now let us focus on the example. Let us focus on the example. This reaction, 2HI gas in presence of gold, Au gives H2 gas plus I2 gas. Now say this is the zero order reaction. That is zero order means if in the reaction vessel, suppose this is the container in which the reaction is carried out, and if in this container, if you will add HI, you will pass HI gas into this, then you will see there is no increase in the concentration of reaction. That is, decomposition is independent of the concentration of the rate of decomposition is independent of the concentration of HI. What is the reason? As already noted above, written above, the concentration always remains at maximum. And therefore, when you add reactant, there is no increase in the concentration because concentration is already at maximum. What is the reason? Just see. Suppose this is the container, this is the reaction container, and this is a gold plate. This is a gold plate. Now, HI gas is split into these spheres denote the molecules of HI. This denotes molecules of HI. These are the molecules of HI. Now see, you know that on the gold surface, on any metallic surface, there exists active center or there exists free valency. And because of this free valency, the surface attract the gas molecule towards itself. Why? Suppose, let us consider any solid, gold or any metal. This is the atom of the metal. Now, this is surrounded by another, this is surrounded by another atom of the metal, like this. This. Uh, so this is the metal, and these are the atoms of the metal. Because metal is in a solid state, so this means the atoms of this solid metal are what to say are tightly packed together, tightly packed. The void between the two atoms in the solid is that almost negligible. Now let us consider any atom in the interior of the solid. You see, this is surrounded by how many atoms? One, two, three, four, five, six atoms. This is also surrounded by one, two, three, four, five, six atoms. This is also surrounded by one, two, three, four, five, six atoms. But you consider any atom which is not in the interior, which is on the surface. For example, suppose this atom. This is on the surface. This is surrounded by only four atoms. This atom. This is also surrounded by only four atoms. This atom. This is surrounded by only three atoms. Or this is surrounded by. This is also surrounded by four atoms. Okay. So what I mean to say that the atom which are present on the surface of metal, they are not completely saturated. Whereas in the whereas in the interior of the solid, each metal atom is surrounded by six atoms. That is, it is attracted by six atoms, but an atom which is on the surface, it is surrounded by only four atoms. This means the valency of that atom which is on the surface is not saturated, is not fully satisfied. This means some free valency, some free attractive force exists on the surface. And because of this attractive force, whenever any gas molecule, suppose this is a HI molecule, when it moves above the surface, it is attracted by the free valency of the surface, like this. And therefore, the molecule of HI get absorbed on the gold surface, absorb on the surface. So here, this is the gold. There are free valencies on the surface, and this free valency that exists on the surface, that this attracts HI molecule towards itself, like this. So HI molecules get absorbed on the surface like this. It is absorbed on the surface like this. Now, the surface is completely, completely occupied by the HI molecules. The surface is completely occupied by the HI molecule. And the chemical reaction, decomposition of HI is taking place at the surface here. About the molecules which are absorbed on the surface, they are reacting, they are undergoing decomposition to give hydrogen and iodine. Now, this surface is completely saturated. There is no vacancy on the surface. Now, suppose, and even after complete saturation of the surface, lot of molecules in the container are waiting to absorb on the surface because they do not get a space to absorb on the surface, so they are waiting. What happens when any molecule, say this molecule, decomposes into hydrogen iodide, this site becomes vacant, and soon some other HI molecule which is waiting, which is in the container, which is still to get a space on the surface, they get absorbed on this. So again, whenever any molecule decomposes, the place left by its decomposition is occupied by another HI molecule. And as a result, the concentration of HI on the surface always remains constant. And reaction is taking place at the surface. Therefore, therefore, the rate of reaction always remains the same. Always remains the same. If you suppose in this container, if you will add what? If you will add HI gas by any inlet, what will happen? The HI amount of HI will increase in the container. But as far as the concentration of HI on the surface of gold is concerned, it will not change because it is already saturated. It is completely covered. There is no space. So the HI you are adding into the container, it is not going to increase the concentration of gold and the concentration of HI on the gold surface. And therefore, we see that no effect of there's no effect of the addition of HI on the rate of decomposition of HI. And we see that this is a zero reaction. So here concentration always remains constant. I think you have understood this. So now let us consider a zero order reaction like this. A, this is, suppose this is R is the reactant, and it is converted into product. Initially, when T is zero, the concentration of R is A naught. Suppose it is A naught. This is concentration of concentration of R is A naught. That is concentration at zero time. And after any time t, after any time t, that is t is equal to t, Initially, the product is zero. And after any time t, suppose the concentration of R decreases from R naught to R naught, sorry, A naught to A, the product concentration is not zero, it is something. It may be A naught minus A, it may be A naught minus A. But what will the actual concentration? That will depend upon the stoichiometric or the chemical equation, whether it is one or two or three, it depends upon that. I simply write that the product concentration is something more than zero, not zero. It is something more than zero. Now, according to the rate, the rate of reaction, the rate of reaction, the rate of reaction. Suppose this is a zero reaction. The rate of, yeah, or you can also write that. Suppose it is the rate of reaction is given by the expression, given by the expression, this is minus dr by dt. Let me change one thing. Let us write this out, and then let us write this out. So this is minus dr by dt, which is the rate of reaction is given by the expression by the dr by dt. This is the rate of reaction at time t because of the concentration at time t. So this is the rate at time t. This is proportional to concentration of this is proportional to this zero. This is concentration of R and eternity. This is this. So we have this is equal to minus this is rate and time t, and this is again this is equal to dr by dt. This is equal to t into t naught r. T naught is zero order rate constant. This is power zero, and anything power zero is one, so this is minus dr by dt. This is equal to k naught. K naught. This is equal to one, and this is k naught. This k naught is a constant. As you see that the rate remains constant, equal to k naught. This is rate, and this is rate constant. They from the unit of since K naught, which is the rate constant of zero order reaction, is equal to rate of reaction. So the unit of rate constant of zero order reaction will be the unit of concentration. The unit of rate constant of zero order reaction, the unit of rate constant of zero order reaction, the unit of rate constant of zero order reaction is the same as the rate of the unit of rate, that is concentration per unit time mission to time inverse. That is mole per liter per second. Mole per liter, mole per liter per second. This is the unit of rate. And this is also the unit of the rate oscillator. Zero. Now let us again come here. From above equation, above equation can be the above equation can be put as minus R. This is equal to K naught into dt. Integrating both sides, integrating both sides, क्या हो जाएगा minus this is sorry VR, this is K naught dt. This is your now this is your minus dr. This is the R concentration R minus this is K naught into T plus a constant plus C, where this is equation number 1. This is index where C is the integration constant. Integration constant initially the integration constant C can be evaluated by applying the initial condition of the reaction. Initial condition is initially when T was 0, initially when T was 0, then R was how much? Concentration R was equal to R naught. R naught. Putting this in the above equation, putting this in the above equation, we get minus R concentration R K naught into T plus sorry, where C is R is where C is the integration constant. Initially when Q are 0, R is R naught. R is R naught. So this is the R naught K0 T and T is 0. So this is K0 into 0 plus C. C is your, this is C. And therefore K naught into 0 is 0. So C is equal to minus R naught. Putting this in the above equation, putting this above equation, putting this in equation 1 means given above, we get what? We get minus R is equal to K naught into T and C is equal to minus R naught. So, so this rearranging this equation we have, if R naught is brought to this side, R naught minus this R divided by T is equal to K naught. So K naught is equal, this is equation number, say this is equation number your 2, and K naught will be equal to how much? This is R naught minus R by T. This is equation number 3. Now, the equation of the graphical representation, the graphical equation, the, the, the equation 2 can graphically be expressed as, be represented as, well, a plot of R. If R sign is changed, this is what? This will be R changing the sign, reversing the chain, minus Q naught into T plus R naught. That is a plot of R versus T can be represented as a plot of R versus T will be a straight line of the slope equal to equal to minus K naught, and intercept equal to R naught as shown below. And shown below. What? This is time. This is time T. And here we are plotting R concentration of reactant. Then a straight line of this type will be obtained. And this is what? This is the intercept. This intercept will be equal to minus K naught. This will be equal to, like, or this is, sorry, a straight line of slope, a straight line of the negative slope. The slope will be negative. Slope equal to, that is, slope will be negative. Slope will be negative. And this is K naught. This is your K naught. Okay. This is K naught. So this is the graphical representation of zero order reaction. Now let us calculate half time, expression for half time. expression for half time T half. When R is equal to R naught by 2, then T is equal to T half. Putting this, in equation 3, mentioned above, we get K naught. This is R naught minus R naught by 2 divided by T half. And therefore T half is equal to R naught minus R naught by 2. This is R naught by 2. 2 K naught. 2 K naught. This is the expression for T half of a zero order reaction. This is the question number 1. Now see, since T half is, since K naught is a constant, so where here T half is directly proportional to initial concentration of the reactant. If initial concentration is doubled, the T half will be also be doubled. If the initial concentration is increased 4 times, the T half will also increase 4 times. So this is all about your zero order reaction. This I'm completing this at this point.